Have you ever wondered why distant car headlights look like a single blur until they get closer? This isn't just a vision problem, it is a fundamental limit of physics caused by the wave nature of light passing through an opening. When light passes through a circular opening, like your pupil or a telescope lens, it doesn't stay in a straight line. It undergoes diffraction, spreading out and creating a specific pattern on the other side. Instead of a perfect point, a point source of light produces an airy disk. This consists of a bright central spot surrounded by concentric rings. Understanding this pattern is key to knowing how clearly we can see. The size of this central disk depends on the wavelength of light and the diameter of the aperture. The first minimum occurs at an angle θ equal to 1.22 times the wavelength divided by the diameter. Lord Rayleigh defined the limit of resolution. He stated that two sources are just resolved when the center of the diffraction pattern of one falls directly on the first minimum of the diffraction pattern of the other. If the sources are closer than this critical angle, their patterns overlap so much they appear as one single blob. If they are further apart, we can easily distinguish them as two distinct objects. When just resolved, there is a small dip in intensity between the two peaks. This dip allows our eyes or sensors to detect that there are two separate sources of light rather than one. To improve resolution, we can either use a shorter wavelength of light or a larger aperture. This is why powerful telescopes have massive mirrors, they need a large diameter to minimize diffraction effects. Let's calculate the resolution of the human eye. With a pupil diameter of 3 mm and green light, the angular resolution is approximately 0.22 milliradians. This determines how far away you can read a sign. Using our calculated angle, we can find the maximum distance at which two headlights appear separate. For a standard car, this distance is roughly 6 to 7 kilometers under ideal conditions. Large telescopes like Hubble have a much larger diameter, d. This results in a tiny angular resolution, allowing astronomers to see distinct stars in distant galaxies that would look like a blur to us. Wavelength matters too. Blue light diffracted through the same hole produces a smaller airy disk than red light. This is why Blu-ray players use blue lasers to read smaller, more tightly packed data on a disc. In microscopy, Rayleigh's criterion sets the limit for the smallest features we can observe. No matter how much you magnify, diffraction eventually blurs details smaller than the wavelength of light used. To summarize, diffraction through a circular aperture creates an airy disk. Rayleigh's criterion provides the mathematical threshold where two objects are just far enough apart to be seen as individuals. Remember, for better resolution, you want a larger diameter or a shorter wavelength. This fundamental limit affects everything from photography and astronomy to the design of our own eyes. Think about the formula, θ equals 1.22 lambda over d. If the diameter d is in the denominator and it doubles, what happens to the angle θ? Take a moment to calculate. Since the diameter is in the denominator, doubling it halves the angle. A smaller angle means better resolution. Thank you for exploring the physics of light with us today. Generated by Vision Solve AI.